So today, let's talk about list, stack, and queue and define them as abstract data types. We will then discuss about arrays and linked lists, which are two other ways in which list, stack, and queue can be implemented. At the end, we'll also enumerate all the implementations possible for list, stack, and queue. And in the future lectures, we will also see how the implementation is done using a programming language like C. Now, as we learned in our previous lecture, an abstract data type is nothing but a mathematical model and some of the operations defined on the mathematical model. Mathematical model is nothing but the data that abstract data type represents. So let's try to define the list as an abstract data type. A list is defined as a collection of elements that can be ordered. The elements can belong to a primitive type, or they can be a complex type, or they can themselves be abstract data types with their own set of mathematical model and operations. When we are saying that the collection is ordered, what we mean is that the element present inside the container is associated with a number, which we generally call as index or ordinal, using which we can order those elements. So what we mean by ordering a collection is that the elements, owing to their mapping to ordinals, can be ordered. So you can say which element comes first, which element comes second, and so on. So each element inside the collection can be represented as a tuple, the first part being the element itself and the second part being the ordinal to which it is mapped. This is slightly different from the concept of sorting, where you arrange the elements or order the elements based on the property of the element itself. So now coming to the operations that accompany the mathematical model, we can define the following operations for a list. The first operation is size, which returns the number of elements present in the list. It returns 0 if the list is empty. The second operation is first. Now this operation first is made possible because the elements are ordered. So you can say, if there are elements in the collection, you can say which one is the first element. And it is nothing but that element which is mapped to the ordinal 1. That's what is returned by first. So if there are two elements T and S mapped to 1 and 2 respectively, T is returned as an output of call. Then you can define the operation last, analogous to first, which is it is last element of the collection, which is nothing but the element mapped to the size of the collection as an ordinal. So if there are 5 elements in the collection, that element which is mapped to the number 5 is the last element. Coming to this operation insert, which is the most interesting one, you can introduce a new element to the collection using insert. Depending on where you insert the element, the insert operation affects other elements of the collection, in that the mapping of ordinals to the other elements of the collection can change. So if you're inserting the element at index 0, all the other elements of the collection will have their ordinals incremented by 1. Essentially, the rest of the collection is shifted right by 1 ordinal. This is because two elements cannot have the same ordinal. So if you're inserting, it's like a slot present, and if you put something in the slot, all the elements starting from the slot that you're putting this element in have to shift by 1 place. And all the elements that are to the left of the index that you're inserting your element in will be unchanged with respect to the mapping to the ordinals. So if there are 10 elements in the collection and you have inserted an element at the 5th index, 5th ordinal, first, second, third, fourth elements don't change. The 5th element is a new element, and the elements that were there in the collection before this element was inserted from the 5th index will have their indexes incremented by 1. So this operation requires that the input index be between 1 and size. You can't insert an element after the last element ends. So I mean, you can actually insert an element after the last element, but not after that. So you can't insert, if there are 10 elements, you can't insert element at 12. You can insert an element at 11, or you can insert an element at 1. So that's the range in which you can have the input index. It returns a false if the index doesn't fall in the predefined range. So the next operation is remove, which behaves the same way as insert, except that it removes the element from the list. Depending on which element is being removed, the removal affects the ordinal mapping of the rest of the elements. So if you remove an element from the middle of the list, all the elements to the left of the list don't change their mapping to the ordinals, they remain the same. All the elements to the right of the element which is being deleted will have their ordinal mapping decremented by 1. So for remove it will be decremented, for insert it will be incremented. Similarly, if you're inserting, the number of elements, total number of elements changes and it is incremented by 1. for remove the total number of elements in the list changes, and that's nothing but the previous size decremented by 1. GetIndex is another useful operation which will give us the ordinal mapping of a particular element t. So it basically looks up for the element and then returns the index mapped to that element. So in this particular example, if you call getIndex on S with the list containing rst, it will return 2 because that's the mapping that element S has. So another useful operation is get element at index, which accepts an index as an input, and it basically returns the element at that particular index. So it's like the counterpart of the get index call. So it'll just look up the collection for the element with the given index. So these are all the operations that are required to define any other operation as well. These are the minimal set of operations that give a full range of operations. So for example, if you want to define isEmpty, that tells if the list is empty or not, you can use the size operation to define it. In fact, first and last are also not needed. You can define first in terms of the get element at index method. Last as well can be defined using get element at index. So these are minimal set of operations which give full power to the developer to define any other operation on top of these. So now let's try to define stack as an abstract data type. Stack is also a collection of items of some type t. Again, t can be a primitive type, complex type, or it can also be an abstract data type in its own right. So the property of stack is that it follows LIFO order when it tries to remove elements from the container. LIFO stands for last in first out, which means that when you're removing elements from the stack, the element that was most recently inserted into the stack is the one that is removed. The model can be represented as a plain sequence of actually a set of numbers, a set of values. So in this particular case, T1, T2, T3 are of type T, and push operation increases the size of the stack by 1. It doesn't tell you how you're going to maintain the insertion order, because to honor the LIFO criteria, you have to also maintain which element was inserted when. It just talks about what's and not hows, basically. Pop is also a similar operation, which basically removes an element from the stack. Again, given example, if there are 3 elements in the stack and you call pop on it, the resultant stack will contain only 2 elements with one of the elements removed, and what element is removed depends on the insertion order of those elements. So if R was inserted the last, that is removed, and the remaining elements are S and T, and analogously you can talk about the other possibilities. So these two are the main operations of the stack. Along with that, you can also define a size which will give you the number of elements present in the stack. And these 3 operations form the minimal set of operations. Every other operation can be represented in terms of these operations. For instance, if you want to get the top element of the stack, you can do a pop, get the topmost element, and push it back again. So top can be implemented in terms of push and pop. isEmpty is again something that you can implement in terms of the size of the function of the abstract data type. Now coming to the definition of Q as an abstract data type. Q is also a collection of elements of some type T. T can be again a primitive type, complex type, or it can be an abstract data type in its own right. It's a FIFO structure, which means that when one tries to remove elements from the queue, the least recently inserted element is the one that is removed. So the first element that was inserted in the queue is the one that is removed. So the model consists of a set of elements. Insert is pretty much similar to the push operation of stack. Delete is different from pop of the stack entity. So delete here removes that element which is the least recently inserted. So it's the element that was inserted the first among all the elements present in the queue at that point in time. So like we had other useful operations for stack, we can also have useful operations for queue as well. isEmpty will tell you if the queue is empty or not. Size will tell you the total number of elements present in the queue. There is no top element in the queue. It's more like you have the queue being changed from both the sides. When you're inserting it at one end, and then you're removing it from the other end, because when you remove it from the same end as you insert it, you're kind of doing a LIFO removal. So you're removing the element that has been recently pushed. So operation top doesn't make sense for the queue. So now let's talk about some implementation details, some possibilities of how you can implement these 3 data structures: list, stack, and queue. The first one is arrays. Arrays is a contiguous sequence of data items or collection of data items. One property is that all the data items that arrays brings together should belong to the same type. And arrays are natively supported in almost all languages. And the most useful feature of arrays is that it gives you very fast index-based access to the elements. So if you want to access, say, 5th element from an array of some size, you can get that element back in a very quick time. It's generally an order of one operation if you're familiar with asymptotic complexities in algorithms, which means that irrespective of the number of elements present in the array, it takes constant time for us to get an element out of the array. So this gives you a very fast index-based access. There are problems with arrays as well. The problem is that the size of the array has to be fixed during the compile time. So you can't have dynamically increasing arrays at runtime. You have to fix the size of the array because this memory location has to be contiguous. The compiler has to know how much memory to reserve for this data structure during compile time. So what happens if the total number of elements increase to such an extent that the reserved memory, contiguous memory, is not enough anymore? That's a problem. I mean, there are ways of resolving the problem by resizing the array. Programming languages provide APIs to built-in functions to resize array, and that's a very costly operation because you have to reserve another contiguous memory location large enough to hold the new size and copy over all the data from the old array to the new array, which is a very costly operation. So this is kind of very inefficient in terms of supporting arbitrary sized collections. It's very efficient in terms of access, very fast ordinal based access, index based access, but not very efficient with respect to memory when you have to increase the number of elements at runtime. So this is primarily useful for cases where you know beforehand the upper bound for the number of elements that can be present in the array. Another alternative that we can use to implement these abstract data type is a linked list. A linked list is basically again a collection like an array, but what distinguishes it from array is that the elements in the collection for a linked list need not be contiguous, so they can be present anywhere in the memory. So that means that the compiler doesn't have to reserve a predefined space, contiguous space. But the way the elements are linked to each other is that the element inside the linked list, each and every element inside the linked list would know what its next element is. So the memory address of the next element of the list is present in the current element. So that way it can kind of you can follow that path of the next addresses of each elements to browse through the elements of the collection. For an array, it is pretty straightforward. It's contiguous, so if you know the size of the element of the array, you can always compute the address of the element inside the array, any element inside the array. But for linked list, you can't do that. So you have to start from the first element, then follow its link to the next element, then follow the link to the next element, and so on to get to the middle of the linked list. So if I have to find out what is the fifth element in a linked list of 10 elements, I have to always start from the first element. So the index-based access is not fast. So it depends on the number of elements present in the linked list and its order of n, where n is the size of the linked list. So if there are n elements in the linked list, you have to perform n operations on an average n operations to get to the element that is needed. But it has advantages. It can support arbitrary size. So if you don't know the number of elements that can be put into the collection beforehand, this is a very useful data structure because there's no resizing required. The elements can be present anywhere and they're linked amongst themselves. It's inefficient in terms of accessing elements based on the ordinals, but it's very flexible in terms of allowing arbitrary sized collections. One other inefficiency that linked list also introduces is an amount of memory required to store the elements. For array, the amount of memory is equal to the size of the element times the number of elements. So if there are 10 elements in the array and each element occupies 4 bytes, all you need is 40 bytes. But for linked list, because you have to have an additional overhead of storing the memory of the next element in each element, you have to incur the penalty of storing the address of the next element in each element. So each element stores the address of the next element. That's the additional memory overhead that linked list introduces. So if you take the earlier example, there are 10 elements and each element occupies 4 bytes, and say address of the next element also occupies 4 bytes. Instead of 10 into 4, 40, you have now each element occupies 8 bytes now because you have 4 bytes of data and 4 bytes of address. So you have 80 bytes. So the size requirement has kind of doubled, even though we are just storing the same number of elements. So that's an additional overhead for a linked list. So to wrap this up, we'll be talking about the following implementations in our future lectures. List can be implemented using an array or a linked list. Stack can be implemented using an array or linked list. Queue can be implemented using an array or linked list. For queue, we can also optimize some of the inefficiencies that are introduced by the linked list based implementation, which we'll also be looking at in the future lectures.